Okay, so now we're getting into the meat of chapter 15 here. We've had a couple lectures already. We did some general carbohydrate discussion in the first lecture. Then we moved on to our discussion of the Fischer projections and how we determine D versus L isomers for the monosaccharides in our previous lecture. So now we're ready to move on with some additional structural chemistry of carbohydrates. In this third lecture on carbohydrates, as you can see, we're going to discuss Haworth structures of monosaccharides. So I don't think we've talked about those just yet. We may have shown them in this section on aldehydes and ketones last chapter, but let's take a look and see what these Haworth structures are all about. If you remember our discussion in the aldehyde and ketone chapter on the idea of either hemiacetals or acetals, well, Haworth structures are the prevalent form of monosaccharides with 5 or 6 carbon atoms. If you remember our last lecture, we said that the most important carbohydrates, or at least the most important monosaccharides, were glucose, galactose, and fructose, and those were all hexoses, 6-carbon sugars. Obviously, when we get into the nucleic acids, I already mentioned that ribose and deoxyribose are 5-carbon monosaccharides, so they're going to be pretty important as well. So these Haworth structures are important here and now for our discussion of carbohydrates, but also when we get into our discussion of nucleic acids in the last chapter of the semester. And they form when the hydroxyl group on carbon 5 reacts with either the aldehyde or ketone group of the aldohexose or ketohexose or aldopentose or ketopentose, depending on if we're talking about a 6 or 5 carbon sugar. So we show the open chain form. It's nice and easy to represent, but it's not really how things are most of the time. 90+% of the time, we'll say the 5 or 6 carbon monosaccharides will form these ring structures, these cyclic hemiacetals, and we see how that happens with that carbon 5 hydroxyl group attacking, in this case it was an aldose, so we have carbon 1 being the carbonyl carbon and then forming this 6-membered ring. It's a heterocycle because one of the members of the ring is an oxygen, a bridging oxygen, instead of being all carbons. Okay, so more about Haworth structures. They are cyclic hemiacetals, and there we see a more common representation. On the previous slide, we were showing you how to get to the Haworth structure, and now you're seeing the Haworth structure in its more usual form. And so they form as a result of that carbonyl group being attacked by the OH group from later on in the same molecule, and when we have a hexose, we have the OH group on carbon 5 react with that carbonyl group, which is on either carbon 1 or carbon 2. And if it's a D isomer, we place that CH2OH, that carbon 6, above the ring. If it were an L isomer, we'd place it below the ring. But because biologically speaking, it's the D isomers of the sugars that are biologically useful, we'll tend to see them mostly with the D forms, and therefore with the carbon group of number 6 up above the plane of the ring. All right, well, hopefully you've gotten used to your Fischer projections by now, because the guide to drawing Haworth structures in step number 1 involves turning that Fischer projection clockwise by 90 degrees, fold that horizontal carbon chain into a hexagon, and bond the oxygen from carbon 5 to the carbonyl group to form the hemiacetal, and then finally complete that Haworth structure by drawing the hydroxyl group on carbon 1 below the ring to give the alpha anomer, or above the ring to give the beta anomer. So we did have alpha and beta on the previous slide. I didn't talk about them yet because I hadn't had a chance to talk about the guide with you, but let's go ahead and take a look at how we put this guide into action. Okay, so here we are in step 1. Turn that Fischer projection for D-glucose clockwise by 90 degrees. So there we have D-glucose, and it's the D form because on carbon 5 we have the OH on the right-hand side, so that's how we know it's the D enantiomer. And of course it's glucose because of carbons 1 through 4. And as we turn it 90 degrees on its side, we see that open chain form would have that appearance. Moving on to step 2, we fold that horizontal carbon chain into a hexagon and bond the oxygen from carbon 5 to the carbonyl group to form the hemiacetal. There we see it, and now we have that hydroxyl group on that new chiral carbon because we've taken that former carbonyl group and now we've reduced it and it gets an OH instead of that double bond O. So there we have it, going from that chain form that we folded on its horizontal to now a ring form with that hydroxyl group on that new chiral carbon, right? It wasn't a chiral carbon before because it was a carbonyl, had 2 bonds to oxygen, couldn't be chiral. Now carbon 1 is now chiral. Okay, finally in step 3 here, we're drawing that OH group on carbon 1. In this case, we've drawn it above the ring, so that's the beta anomer. If we had drawn it below the ring, as we see on the left-hand side, it's the alpha anomer. So depending on where that relative position is, and we can pick carbon 1 out quite easily here for an aldo hexose because carbon 1 is going to be bonded to that oxygen in the ring, and then of course we have on carbon 5 we have the carbon 6 coming off of the ring. So hopefully, if you haven't already caught on, that's a key structural feature that'll help you find carbon 1 and therefore help you determine if you have the alpha anomer if the OH group is down below, or the beta anomer if the OH group is up above the ring on carbon 1. Since this has all been so easy, hopefully I hope you found it easy. I'm a little more practical than that, and it's probably already pretty confusing. Well, let's confuse it even more, right? Let's talk about mutarotation of alpha D-glucose and beta D-glucose. So the process of rings opening and closing is called mutarotation. So it's a fun word, a good word to show off to your friends and family now that you know what that means. Be careful who you say it to. You might end up talking to a chemist and he or she may grill you on it, but among non-chemists it's a pretty impressive word. So both anomers are converted to the open chain and back to a cyclic hemiacetal, so we can actually go between the two forms. We have an equilibrium set up. So the alpha D-glucose is the less preferred form of the ring form. The open chain form, there's only very little. As you see, the open chain D-glucose is a trace amount, but it's important because it's that trace amount that allows for moving back and forth in our dynamic equilibrium. And then finally, the beta D-glucose is the predominant form. It's 64% in our equilibrium mixture. So there we have it. Glucose appears in all 3 forms at different times and in different amounts, but averaged over that dynamic equilibrium, we tend to have very little, less than 1% in that open chain form, most of it in the beta form, beta D-glucose, the beta anomer, with that OH group above the ring, above just like carbon 6 there is above, and roughly a third of the time, 36% of the time, we have the alpha anomer where the OH group is below the ring and the carbon 6 there is above the ring. So there we have it. We can go from one form to another, but it tends to be predominating in the beta anomer for D-glucose in its ring form. We've focused so far on glucose. Glucose is one of our very important monosaccharides. Let's talk about the Haworth structures of fructose now. Fructose, as opposed to glucose, which is an aldohexose, fructose is a ketohexose. So it forms Haworth structures when the OH group on carbon 5 bonds to the carbonyl on carbon 2, right? We were still an OH group on carbon 5 for our glucose example, but it was the carbonyl on carbon 1. Now it's the carbonyl on carbon 2. And if you notice, that gives a 5-membered ring instead of a 6-membered ring. So there we see the alpha anomer, where we have that OH group down below the plane and carbon 6 up above the plane of the ring. And then we have the beta anomer, where the OH group is up above, just like the carbon 6 is up above. So the beta and the alpha anomer stuff is still the same rules as for glucose, but the ring is different here for fructose because it's a 5-membered ring as opposed to a 6-membered ring. Also notice here carbon 1 is off the ring. It's not on the ring like in the case of an aldohexose, and carbon 1 is not chiral because it has 2 hydrogens on it. Okay, let's pause here for a learning check. Let's see how you're doing. We've looked at a couple different Haworth structures. We've looked at the Haworth structures of D-glucose, and now just more recently D-fructose. And so now your challenge here in this learning check is to draw the Haworth structure of alpha D-galactose. And there we have the D-galactose structure. So hopefully you can apply those different steps from our guide, and in those 3 steps arrive at the alpha D-galactose. So pause the video here while you complete those steps, and then start us back up when you're ready to check your work. Okay, there we have it. Hopefully you were able to do this well, right? Step number 1 involved taking that open chain Fischer projection and rotating it clockwise by 90 degrees. So there we have what you should have arrived at for the result of step 1. Now in step 2 here, you fold that horizontal carbon chain into a hexagon and bond the O on carbon 5 to the carbonyl group to form the hemiacetal. Of course, this structures an aldohexose, so it's going to look a lot like the glucose in how we form that cyclic hemiacetal structure. And finally, here in step 3, you complete the Haworth structure by drawing the OH group on carbon 1 below the ring to give the alpha anomer, or of course above the ring to give the beta anomer. But since we asked for the alpha anomer, this structure with the OH group below the plane is the correct form. So hopefully you arrived at that. If you did run into trouble, please do try some additional practice problems. And certainly if you're continuing to run into trouble, do reach out to me. Of course, I would give you the Fischer projection before I ask for the Haworth structure, but if you're running into trouble starting from there to get to that Haworth structure, please do reach out to me. I would never expect you to come up with everything from scratch, but getting there from the Fischer projection, if that's troubling you, then please reach out. If not, if things are going well, as I hope they are, we'll see each other in the next lecture.